Okay, so I suppose that everyone who wants to be here is here. Are there any newcomers this week comparing to the last one? I think there should be a few people who are new. And please let me know, by the way, if you can hear me. That's cool. So let me start the recording. Can I start the recording? No. Teams is a little bit complicated if I want to join it not from the right team. Give me one more second. Yeah, so somebody is saying that he cannot hear me. That's bad. Oh, okay, that's good. Okay, so I started recording. Okay, so now everything seems to be good. So thanks for joining today. And the main thing that we will be doing today is the continuation of Lab 1. So let me, first of all, let me clarify a few things for those who are new. For some reason I cannot start recording. Why is that? Okay, now it seems to be recording. So for those of you who are new to this class, by the way, I'm not sure that everyone is here who is supposed to be, because in the Telegram chat we have about 20 people. They've been, and at least the group, I think there are about 20 people. So I wonder why do we have less participants here. But anyway, so I will make the recording and hope that everyone who wants to attend the course will follow it. So I remind you that we started the course in the beginning of September, and we had a couple of, actually we had one, so join later, you should definitely watch it. And then last time we started doing the first part of Lab 1. The link to the lab is available inside Teams. It's a GitHub Classroom, so you enter it creates the repository for you. You clone that repository, and then you work on your solution inside that repository, and you check it in. And then after you finish, you provide the link to the repository for me to check it inside Teams. So in Teams, let me share my screen. And so just to make sure that everyone is clear, we have the team group in Teams, functional logic programming. And here we have class list. And in the class list, there is the column called Lab1 link, and I expect you to provide a link here to the GitHub repository of your first lab. And once you do that, I will spend some time and check it and provide you feedback as GitHub issues. So today, I expect you to continue working on the second part of this lab. So the first part of the lab was to compute the function using Taylor series. You were asked to add, to basically to repeat the exercise which we did during the lecture. However, in slightly more complicated form, because during the lecture we just added first n terms, and here you should add terms until they become sufficiently small. So definitely finish the first of the lab today, and also work on the second part. And I will talk about the second part of the lab in a few minutes. And first of all, please let me know if there are any questions, if you had any complications working on this first part of the lab, like how was this exercise? Did everybody manage to set up F# environment?
And where can I find the link of the GitHub?
The link, okay, the link to GitHub Classroom, it should be somewhere in the chat. Let me. Actually, instead of looking for it, let me give you the link. I will put the link in the Teams chat. Okay, so yeah, somebody was already did that. Okay, so you have the link to the GitHub Classroom. You go there and you have the repository and you start working on it. So any questions you had during this? Any questions you have? Anybody succeeded, like finished and ready to start with the second part? Raise your hand so that I know that you hear me and everything is good. Okay. Then let me tell you about the second part of the lab. The second part of the lab is about solving equations numerically. So here you would have a transcendental equation, meaning the equation which is not easy to solve using traditional methods, but they can be solved numerically. And each of you would have 3 equations to solve. So if you open this PDF file, this is the text couple of paragraphs, but everybody has the equations defined here in the table too. So you take 3 consecutive equations starting from the number that you have in the list. So for example, if your number is number 5 in the list, you take 5, 6, and 7. And each of the equations has the interval at which you should look for the solution. So for example, number 5, you should look for the solution in the interval from 0 to 1. And the solution is approximate solution is given here so that you can check if you get the right result or not. And you should solve those 3 equations using 3 different computational methods, namely dichotomy, iterations, and Newton. And I will talk a little bit about those methods in a second. So because you need to solve 3 equations using 3 methods, it's obvious that you should probably define the generic function to solve the equation using each of those methods, and then just provide different functions as arguments. And that is like the main exercise here, so that you get used to passing functions as arguments to other functions. And so that's the main idea. And also, as we will learn in a minute, the Newton method is actually one specific case of iterations. So in fact, you would probably end up implementing Newton method as the case of iterations by calling the same function you developed for iterations. So let me tell you a little bit about the methods themselves. So the first one is dichotomy. That is very simple method. So it applies to the equation, like suppose you have certain function f of x in the interval from a to b, and your goal is to find the root, this one. So dichotomy can be applied to any function f which is continuous, and which has exactly one root on the interval. And in your case, it is the case. You have equations with exactly one root on the interval. If this is the case, in the signs of the function on different ends of the interval would be different, right? So f of a multiplied by f of b would be less than 0 if there is exactly one root on the interval. So what would be the easiest way to find the solution? You do the bisection. You calculate the middle of the interval. So let's say you would start with a0 equals a and b0 equals b, and then you calculate the middle of the interval, which is c, which is equal c0 equals to a0 plus b0 over 2. Well, actually, I can put I here. So for any iteration, you do the same. You calculate the middle of the interval, and then you see at which of those intervals the solution lies. That's easy to know, because if you multiply f of a times f of c, if it's less than 0, then root is in the interval from a to c. If it's more than 0, then it's the root is not on this interval. So you select as the next interval, you select this interval from a to c, and you repeat this procedure. You calculate the middle of the interval again, and by doing so, you quickly narrow the interval. Each time it becomes like twice shorter. So very soon you end up with a very, very short interval on which the solution lies, and that would be your approximation of the root. So for you, when you look for the solution, you wants to achieve certain accuracy. Let's say you want to calculate the solution up to the precision of 10 to the power minus 5. In this case, if the length of the interval becomes less, it means that you have found your solution. So this is very simple method. It works very well for almost all of the functions. So what you should do, you should define the function dichotomy, and you would pass probably the function f, and then the interval from a to b, and it would give you the root x. And by providing it with 3 equations, you would end up getting the solution, right? So this is pretty simple. Now, the disadvantage of this method is that even though it's fast, and especially for those simple algebraic equations, it would be very fast, but in the general case, it does not converge. Sometimes it converges slower than you want, and that's why we want to have some other methods for solving equations. And the second method is called iterations. And the idea of this method is that you rewrite the equation in the different form. So you represent the equation in the form x equals some function phi of x. It's basically like you can do it in several ways, but try. So for example, if you have the equation like this, like number 5 here, you can say that, well, number 5 is kind of more difficult. Let me take some easy one. Is there an easy one? Yeah, for example, this one, x minus 2 plus sine 1 over x. So you can, so if you have the equation x minus 2 plus sine 1 over x equals to 0, so you can say x equals 2 minus sine 1 over x. And this would be your function phi of x. Or you can say, of course, you can express it differently as well. So if you can say, for example, sine 1 over x equals 2 minus x. So x would be 1 over x sine 2 minus x. So something like this. You can do it in different ways and see which one works, basically. So if you have written your equation in this form, then graphically it means this. Graphically it means that you need to find the solution where the function intersects with y equals x line, right? So this would be the graph of phi of x, and this would be the graph of the line phi of x. And you need to find this point of intersection. So to say it in other words, if the equation looks like this, x equals phi of x, it means that we are looking for the fixed point of this function phi, right? The fixed point is the point which is not changed by the function. And one of the ways to find the fixed point is to start with some arbitrary number. So I would start with any number x0, and then I would compute x1 as phi of x0, x2 as phi of x1, and so on. So each time I basically take some number x, some number x, and I apply the function. So if I apply the function graphically, it means that like this is the solution I would get. So this would be phi of x0. And if I want to put this as an argument to the function again, it's basically I'm looking for this. This would be x1. And I would put it into the function again, and I compute the phi of x1, which is x2. This would be x2, and so on. So basically, I'm walking in the direction of this intersection pretty fast. So that would be the iteration method. The problem is that it does not always converge, because sometimes it can happen that, for example, if you draw a function like this is y over x, and suppose you draw it like this, and you have your interval somewhere here, and you start at this point. So this would be your x0. In this case, it would not converge. It would, in fact, diverge, which is not good. So sometimes you need to play a little bit, selecting different ways to rewrite the equation in this form, because the original equation that you are given is in the form f of x equals to 0. So if you want to rewrite it, you can either write it in the form x equals x plus f of x, or in many other ways. Mathematically, there are criteria for when this method converges. Namely, it converges if the derivative phi prime of x is less than 1. The absolute value of the derivative is less than 1 on this interval. But yeah, you can try calculating the derivative or just give it a few tries. It's also important which first number, from which number you start. Because, for example, here, if you start from x0, it's good. If you start from the number somewhere in this area, it would probably diverge. So try a few different starting points, try a few different ways to represent the function, and some of that would probably work. And more details, like if you want to learn more details on this method, you can find the description on Wikipedia. It basically repeats what I'm saying. You write the equation on this form, look for the fixed point, and do the iterative process like this. And finally, the third method is some specific way to look for this function phi. So let's again consider our initial initial equation f of x equals 0. So this is Newton method. Again, we have this function f of x, and we are looking for the root here. So for this point. Again, because this is essentially the iteration method, we start with some number x0. And how do we look for the next point which is very close to the root? Because the function can look differently, we can approximate the function here as the tangent. So if we draw the tangent here, the tangent would then intersect the horizontal x-axis at some point. And this would be our next x1. And then we repeat this again. We take this point, we draw the tangent, and we get the number x2. And so on. So that's basically how we arrive at the Newton method. How do we calculate this function x1? So the equation for this tangent would be, what would be the equation for the tangent? So it would be y equals f prime of x times x, and we need to find, well, actually, I will not repeat the whole derivation. I would also, I think, refer you to Wikipedia for simplicity. Yeah, that would be the formula for computing. This would be the formula for computing the next value of x. So x n plus 1 equals to previous x n minus f of x n divided by f prime of x n. The problem here is, first of all, you need to know the derivative of the function. And secondly, because you divide by derivative, this derivative should not be sufficiently small, because if derivative becomes 0, which means that the function becomes always horizontal, the method doesn't work well because the line hardly intersects with x. So in this case, probably what you would need to define, you would need to define the function Newton, and you would pass f, you would pass f prime as an argument, and the starting point x0. And it would give you x. And your goal, because it is the special case of iterations, you would probably define this function Newton based on the previous function iteration that you defined earlier. And the iteration function would look like that. You would say iteration, you would pass f, and you would pass x0, and it would give you the root. So that's basically the what you need to do for the lab. And that should be pretty straightforward, but still it would take you some time to achieve that. So at the end of the lab, you should print out the table of 9 numbers. So each of you should solve 3 equations. So it would be 1 to 3 number of equations, and then you would have roots by dichotomy, by iterations, and by Newton. Table of 9 numbers. So that's basically it. I think that would be the goal of the lab today. And if you have any questions, let's ask now, or you are always welcome to ask me in Telegram chat.
Excuse me, but we have only one equation near our surname. Where can we take other two?
You take 3 consecutive equations. Like if your number is 5, you take 5, 6, and 7.
Okay. And each equation we should solve by all 3 methods?
Exactly.
Okay.
And that's why you end up with this table with 9 solutions. And those solutions would be the same, of course, for each, well, not those solutions, but those solutions for each equation should be the same.
Thank you.
So the goal here is not so much to exercise in numerical computations, but to be able to realize that it's easy to pass functions inside other functions, and how to reuse code. For example, once you define the method for iterations, the Newton can be just reduced to that function. You don't need to define this again. So iteration would probably be a recursive function, right? Because you would apply it over and over again until it reaches the good accuracy. And by the way, how do you know when to stop this iteration method, for example? When xn plus 1 minus x of n becomes sufficiently small, when it's smaller than some number of epsilon, which is the precision. So everyone good? You know what you are doing, and yeah, please try to do this today. I don't know if I should also give you some theoretical material today, or we will do it next week. Probably I will actually I will send I'll probably not give any additional theoretical material for today. I will point you to the first part of the lecture, which is available in Russian, just in case you want to go like a little bit in more detail. And for those of you who just joined this course this week, you take this time to catch up. So I would expect that everybody who is doing this course is up to speed and finish this lab pretty much today, so that you don't have it, you know, that you finish it and you forget about it, and next week we will move on to the next topics. So everybody is clear on what we are doing today? Okay, so today I will leave you with this exercise, and we don't meet like online together anymore. You just complete the exercise, you check it into GitHub, you provide the link in the repository, and link would be just one for both exercises because it's the same lab. And that's it for today. And I will leave you with some links to Russian video lectures in the chat. And next week, please come with any questions that you might have on this. So we will.
Excuse me, will we still have today the practical exercise?
Oh, this is your practical exercise. This is your practical exercise. Take it and use both slots of the time to finish this. Like
okay,
the rest.
So we won't have lecture and we won't have the practical exercise.
Yeah, this is the practical exercise. You would have 2 practical exercises today, and next time you would have material for the lecture.
Okay.
I do not think that we should, like, I do not always separate very strictly between lectures and practical exercises, because lectures would mostly be online. So I will provide you materials and you watch it like whenever you have time. And practical exercises are like this. You do them on GitHub and check in the results and ask questions.
Sorry, can you repeat the time of deadline for this lab?
So let's say that deadline would be next week. So like today, probably it's the good idea to finish it today. But if you, for some reason, if you cannot, then the deadline would be next week. And I will, for clarity, I would put it as an assignment in Teams so that you see the deadline there as well. So let me see, 29th. Okay, everybody is clear on what we are doing. Any further questions, comments? Okay, then if there are no questions, comments, I will leave you with this assignment. Again, questions in Telegram channel, and try to check in the final solution today. And with this, yeah, probably I would wish you a good day, and that's it. Okay, goodbye.
Okay, goodbye.
Thank you. Goodbye.